Hello, and thank you for joining us for the rollout workshop of ProTreat and SulfaPro version 7.0. There are a lot of exciting new features and some great improvements to go through, and I hope you all find something here that helps and improves your use of the software. Hybrid solvents is a new thermodynamic model implemented in ProTreat version 7.0. Blends are retrofitted data composed of MDEA or DIPA amine loaded with sulfolane, with or without piperazine. Sulfolane hybrids is offered as an add-on package under a separate subscription fee. Other hybrid solvent blends will be expanded in future software releases. Hybrid solvents combines chemical and physical solubility for optimum gas treating performance into a single solvent. Chemical solubility, which primarily controls H2S and CO2 removal, is provided by the aqueous portion, MDEA or DIPA-based amine component, and the addition of piperazine increases solvent reactivity, mainly for CO2. Physical solubility, which primarily controls weaker acids such as mercaptans and COS, is provided by the aqueous sulfolane component in the blend. Sulfolane behaves as an organic solvent. In addition to mercaptans and COS, other heavy hydrocarbons and BTEX aromatics are also co-absorbed. Sulfolane hybrid blends are specifically formulated according to the gas treating objectives and the quantity of H2S, CO2, COS, and mercaptan species present in the feed gas. Higher H2S and CO2 content in the feed gas require a higher MDEA or DIPA strength and or a higher solvent circulation rate. Higher COS and mercaptan content in the feed gas require a higher sulfolane strength and or a higher solvent circulation rate. However, this comes at the risk of higher coabsorption of heavy hydrocarbons and BTEX aromatics with higher solvent strength and circulation rates. Piperazine is added to the blend to enhance CO2 and COS removal. This comes at the expense of losing H2S removal selectivity. Sulfolane hybrid blends are part of Shell's gas treating technologies with proprietary solvents marketed under various sulfonol trade names: sulfonol D, which is a DIPA sulfonol blend, sulfonol M, which is an MDEA sulfonol blend, and sulfonol X, which is an MDEA piperazine sulfonol blend. Formulation specifics are confidential to Shell. However, per the references below, the blend consists generically of equal parts base amine, which is MDEA or DIPA, and sulfolane, with a smaller content of piperazine if it's required. The remaining component is water. Note that water content on the hybrid solvents is much less compared to the standard standalone generic MDEA or DIPA aqueous chemical solvents. The remaining slides show a case study for treating a sour fuel gas stream. Fuel gas flow is 20 million standard cubic feet per day at 185 pounds per square inch gauge and 110 degrees Fahrenheit, containing 4 mol percent H2S, 1.49 mol percent CO2, and 0.03 mol percent equal parts of C1 through C4 mercaptans and COS. 2 simulations were performed, one with trays at 3-inch weirs, while the other is a 20-foot number 2 random packed absorber. On both cases, the absorber flooding was set to 70%. The study solvent circulation rates were set to 120 GPM on all simulations along different formulations with and without piperazine. Typical generic MDEA and DIPA aqueous strengths are included for comparison purposes. The simulation flowsheet is very similar to the classic modeling of any generic amine unit, with paired amine absorber and stripper columns. The peculiarity here is that all calculation blocks in the simulation are set to use the sulfolane hybrid thermodynamic package. Other thermodynamic packages in ProTreat are OGT thermo and physical thermo. They will not work properly when the blends are involving sulfolane. This slide tabulates H2S, CO2, COS, and mercaptans removal for the trade absorber case. Hybrid solvents A, B, G, and H are all MDEA DIPA blends with sulfolane spiked with piperazine to enhance the H2S, CO2, COS, and mercaptans removal. Generic iconic MDEA or DIPA solvents E and F exhibit poor performance for COS and mercaptans. Hybrid solvents C and D are blends with sulfolane and dramatically improve mercaptans removal. The COS enhancement is negligible for these, however. As expected, mercaptans removal improves when blending with sulfolane. Heavy molecular weight mercaptans, such as butyl mercaptan, are easier to remove compared to the lighter molecular weight methyl mercaptan. MDEA, being a tertiary amine, presents a better H2S selectivity towards CO2 absorption compared to the DIPA, which is a secondary amine. This slide tabulates H2S, CO2, COS, and mercaptans removal for the packed absorber case. The same recoveries observed for the trade absorber simulations are also observed for the packed absorber. However, their magnitude is much less because of less holdup time, which is typical of the packed tower compared to the trade design. Lower contact time between the vapor and liquid phases translates into less recovery. So to wrap up the hybrids portion, the hybrid solvents combines the best of two worlds: removal of H2S, CO2, COS, and mercaptans by both physical and chemical functionalities. Solvent formulations are case-dependent, and they are typically tailored to the feed composition and the desired performance specifications. A single formulation does not fit all gas treating situations. Practically in all cases, H2S is completely removed. Generic chemical solvents are poorly situated for mercaptan and COS removal because these components are weaker acids compared to the stronger H2S and CO2 acids. Mercaptans removal improved substantially when considering a hybrid solvent and further enhanced when adding piperazine. In contrast, COS removal improves marginally when introducing sulfolane. Trade and packed absorber performances present very different mass transfer characteristics. Trays have a much larger residence time for the vapor and liquid phases to contact compared to packing, despite the packing having a larger contact area. In this case, the kinetics-controlled absorption, such as COS, the trade absorber showed better recoveries compared to the packed designs. Dipisulfolane blends present slightly better methyl mercaptan removal compared to MDEA solvent blends. A higher percentage of recoveries are expected for heavier mercaptans. They are easier to remove when considering hybrid solvents compared to lighter mercaptans. Removal efficiency controlled by physical solubility are pressure dependent. Higher pressures favor COS and mercaptan absorption. Higher removal is expected as the contactor operating pressure increases. Watch out for excessive heavy hydrocarbons and PTEX aromatic coabsorption, since this could lead to foaming events. Adjust the sulfolane content in the blend to limit undesired hydrocarbon absorption. Blend amine contents might change due to vapor pressure and mechanical losses. Continuously monitor these strengths of each amine species in the blend to achieve the optimum removal. We have updated the COS component to now include rigorous rate-based reaction kinetics, which allows for a much more accurate prediction for the removal of COS with aqueous amine and hybrid solvents. This model has been validated against several sets of actual plant data to ensure the highest level of accuracy. There are two reaction sets shown here. The first is the general reaction kinetics model for tertiary amines. These amines do not react directly with COS, but rather act as a proton sink, similar to the reaction kinetics of CO2 with tertiaries. Because of this, the reaction rate in tertiary amines is quite slow. The second reaction set is for the COS in primary and secondary amines. These amines do react directly with COS to form thiocarbamates, making the reaction rate faster than tertiary amines, but the COS reaction rate is still much slower than even CO2, as you will see on the next slide. This slide shows the performance of DEA and MDEA in removing COS from a feed gas containing about 500 ppm COS along with CO2 and H2S. It can be seen that the removal of COS is much more effective with DEA than it is with MDEA. DEA removes about 65% COS in the feed gas as opposed to 23% by MDEA. This is because DEA, a secondary amine, is a thiocarbamate former and reacts much faster with COS than MDEA does. The table shows the comparison for the legacy ProTreat model against the newly implemented kinetic model. The legacy model treated COS as a physical component, meaning only what was physically dissolved was removed. Thus, it removes almost no COS. In addition, the plots below the table show COS and CO2 partial pressures in the absorber trays for the two amines. The gentler decrease in COS partial pressure reflects the much slower reaction kinetics of COS compared with CO2. COS is severely mass transfer rate limited in a typical amine absorber. It's imperative that a mass transfer rate-based model be used to reliably predict the removal of COS. Continuing on with the additions, we have added a number of Dow Eucrosol solvent offerings. This list provides the vast majority of the solvents available from Dow. These solvents complete both the HS and AP series of solvents in ProTreat, as well as bringing in the LE series solvents. The sulfur converter block has had a complete overhaul, which brings in a host of new capabilities. The dialog box has been completely reworked to allow for the inclusion of several important elements. Once the dialog box has been opened, the first tab you come to is the overall reactor specifications. These include the thermal specifications, where you select what thermal mode you want, the pressure specifications, where you specify how you want the pressure to be specified, the reaction specifications, where you select how the reactions will be calculated, and the vessel specifications, where there are some options for how to size or rate the vessel. The pressure and reaction tabs have additional options for being specified by section, and we'll discuss more of that in a moment. Moving over to the section data, this is where you specify each individual section within the vessel. Here you can add, duplicate, remove, or move each section. Within each specific section, you can select the type of catalyst that that section has and the specific size of that layer. The reactions and pressure tabs have the option of either being specified from the overall vessel calculations or by each individual layer. If you selected for them to be by section in the reactor data section, those specifications will be made here rather than back on the overall vessel specifications area. Titania catalyst has now been added and support has been included to allow for multiple layers of catalyst to be included in a single converter vessel. For example, you can now put in the activated alumina layer, titania layer, and even the support layer. The converter now has the ability to calculate the pressure drop through the catalyst bed. This, combined with the pressure drop calculations from other equipment pieces, helps to give a much better pressure profile through the train. There is a new sulfur equipment piece, the hydrogenation reactor. This reactor includes support for the first generation cobalt molybdenum catalyst and uses a rigorous reaction kinetics model, similar to the Claus converter. The hydrogenation reactor includes the ability to model both hydrothermal aging as well as poisoning in the catalyst, and helps to accurately and reliably evaluate the effects of unit performance based on real-world conditions in the plant. Similar to the Claus converter, this vessel allows for multiple layers, although because only one active catalyst type is available at this time, the layers would include the active cobalt molybdenum catalyst and the inert support layer. Pressure drop is able to be calculated through the catalyst bed, and advanced sizing and rating calculations can be done on the vessel. The dialog box is quite similar to the Claus converter dialog, with a few exceptions. The overall reactions tab includes the reaction set for a hydrogenation reactor, whereas the Claus converter only contains the reaction set for a Claus converter. Under the section data and basic data, there are two options for setting the age of the catalyst and the poisoning of the catalyst. You can set the age of the catalyst by selecting the button to the right and specifying how many months that catalyst has been in service. That will correspond to a specific aging value. Similarly, you can set the catalyst poisoning by service. These include several different options, whether the heat source is from a burner, and if that burner is using refinery gas, how much air is being slipped, or excess air, whether the unit is using reformer hydrogen, how much BTEX is coming in, and whether acid gas enrichment off gas is being put through the vessel. Each of these will correspond to a specific poisoning parameter. There have been some significant improvements to the program's interface. The Flowsheet's convergence dashboard has now been completely integrated so that everything now resides within a single window. No more annoying pop-ups. This helps the user easily monitor the progression of the flowsheet. The convergence dashboard now shows at the bottom of the flowsheet by default and shows the block solving sequence, the recycle convergence, the simulation status, and the column convergence. This new window, as well as the stream table and the flowsheet, can all be minimized, closed, docked to a specific place, or floated to give the best user experience. There are several other items of interest as well. I have them all listed here, however, I'll show each one individually. You can now switch between zoom levels on a flowsheet by holding Control and using the mouse scroll wheel. In previous, you had to come up to the object palette and select it from the drop-down. You can now hold the spaced key to insert multiple instances of a selected block. For example, if you had 5 inlets that you wanted to put down, instead of continually coming up and clicking, you can select the inlet, hold down the space key, and put down as many inlets as you need. This applies to all the blocks on the object palette. You can now drag to reorder the components in the Components Manager. So say if I wanted hydrogen sulfide to come before carbon dioxide, simply hold it down and drag it to above. You can now drag to reorder streams in the stream table. So say for example, I wanted stream 3 to come before stream 1. I would simply grab stream 3 and move it to before stream 1. We've implemented a new file auto backup and recovery system. This can be found in Setup and Preferences. This allows for a series of files to be saved so that if unwanted changes are made and mistakenly saved, the original file can be recovered. So if we enable the auto recovery, we can select to automatically create that recovery file on a save. And we can additionally have this file saved every so often, and we can select to store up to X number of files depending on your preferences. Changes that are made to the units in the results file, or PTR, are now saved and translated back to the drawing file, or PTD. So say for example, I calculated all my streams in degrees Fahrenheit, but I want to change that and see it in degrees Celsius. And I want all subsequent simulations to be in degrees Celsius. So if I change that here, select OK, save, and then flip back, now every subsequent run will be reported in degrees Celsius rather than degrees Fahrenheit. For Sulfur Pro, OGT has implemented some new additions to the burner block. Fired reheaters have similar reactants as reaction furnaces, but with even less residence time to allow kinetically controlled reactions to proceed. The Reaction Control tab in the burner block allows sufficient control to address two of these reactions: the thermal cracking of H2S into hydrogen and sulfur, and the Claus reaction. In real life, the two reactions listed above proceed somewhere between not at all to reaching equilibrium. The exact extent of the reaction depends on the physical dimensions of the burner, and the kinetic data are sparse or non-existent. ProTreat gives the user options to limit either or both of the above reactions to match plant data and perform sensitivity studies. The Override Equilibrium with Reaction Controls checkbox enables the options to either use the partial approach to equilibrium for all reactions or the acid-gas-fired reheater reactions. The partial approach to equilibrium for all reactions radio button can be used to specify a partial approach to equilibrium for all the reactions in a percent or fractional basis. The acid-gas-fired reheater reactions checkbox presents a pair of checkboxes: one for H2S conversion by thermal splitting, and H2S conversion by partial oxidation followed by Claus reaction. These enable the user to turn on the controls for either or both of the reactions. Each of the two reactions can be individually specified by approach to equilibrium or conversion of feed H2S. In addition to these reactions, the air supply can be calculated for a specific temperature. In the software, under the Air Supply tab, the burner block can now calculate an airflow, either excess air or substoichiometric air, to meet an outlet temperature. Specification of either of these radial buttons will perform the calculation. Sulfur recovery and conversion tables can now be calculated and specified in Sulfur Pro. The sulfur recovery table is a block that allows the user to flexibly calculate atomic sulfur recovery. In the block, the user is able to define any number of recovery calculation stages by selecting unique feed and product streams for each stage. The block will then calculate the recovery of each individual stage, as well as the overall recovery for all stages up to and including the stage of interest. The amount of recovered sulfur is calculated by considering the total amount of sulfur in the liquid phase, while the amount of feed sulfur considers all the atomic sulfur in the given stage feed streams. The user has the additional option of selecting Include Only Elemental Sulfur in Liquid Product Streams. If selected, then the product recovery of each stage will be calculated by only considering liquid S2, S6, and S8 instead of all atomic sulfur. The equations used to calculate stage and overall recovery are as seen on this slide. Once the recovery table has been placed on the flowsheet, you can double-click on the top to open up the dialog box. The Reference Feed Streams tab allows the user to select reference streams that are used for the overall recovery calculations. Recovery streams are typically selected to include all the feed streams to the SRU. This ensures that overall recovery calculations are carried out with respect to all sulfur entering the unit. To select a reference feed stream, highlight a stream from the Available Streams box and move it to the Input Feed Streams box using the double-sided arrow button. The Stages tab allows the user to create any number of calculation stages and gives the user the flexibility to define those stages as desired. The Add Stage and Remove Stage buttons are used to create the appropriate number of stages. The Move Up and Move Down buttons are used to change the order that the stages appear, which impacts overall recovery calculations. If calculating the overall recovery across multiple stages is important to the user, then the stages should be listed in the same order as they appear in the SRU. For example, if you have 2 converter stages and 1 thermal stage, then you should have the thermal stage, stage 1, and stage 2. Once a stage is created, the feed streams and liquid product streams for that stage can be chosen by highlighting streams under the Available Streams box and clicking the appropriate double-sided arrow button. If the user would like to use the reference streams defined in the Reference Streams tab, then the checkbox Feed Streams Same as Reference Feed Streams can be chosen, which automatically populates the feed streams with the reference feed streams. When selecting stage feed and product streams, the user should take care to ensure that these values are appropriately selected. In this particular example, a sulfur recovery table is used with a single converter stage Claus unit. Here, the reference streams are chosen to be 3 and 23 since they are the feed streams to the overall SRU. In thermal stage, stream 3 is selected as a feed stream, and streams 6 and 9 are selected as the liquid product streams. 6 comes from the waste heat boiler, and 9 comes from the thermal stage Claus condenser. In stage 1, stream 10 is the feed stream, and stream 13 is the liquid product stream. For this case, the Include Only Elemental Sulfur and Liquid Product Streams checkbox is selected. The results show the recovery of elemental sulfur for each stage, as well as the cumulative recovery with regards to the reference streams. The sulfur conversion table is much like the sulfur recovery table. However, instead of calculating how much sulfur product has been recovered, the conversion table shows how much of the incoming sulfur has been converted to elemental sulfur. The sulfur conversion table is a block which allows the user to flexibly calculate atomic sulfur conversion. In the block, the user can define any number of conversion stages by selecting unique feed and product streams for each stage. The block will then calculate the conversion of each individual stage, as well as the overall conversion for all stages up to and including the stage of interest. Both the feed and product of each conversion stage are calculated by considering only the total amount of non-elemental sulfur. Therefore, S2, S6, and S8 are excluded in these calculations. The equations used to calculate stage and overall conversion are on the screen. As with the recovery table, once the conversion table has been placed in the flow sheet, double-click to open the dialog box. The Reference Feed Streams tab allows the user to select reference streams that are used for overall conversion calculations. Reference streams are typically selected to include all feed streams to the SRU. This ensures that overall conversion calculations are carried out with respect to all non-elemental sulfur entering the unit. To select a reference feed stream, highlight a stream from the Available Streams box and move it to the Input Feed Streams box using the double-sided arrow. The Stages tab allows the user to create any number of calculation stages and gives the user the flexibility to define stages as desired. The Add Stage and Remove Stage buttons are used to create the appropriate number of stages. The Move Up and Move Down buttons are used to change the order that the stages appear, which impacts the overall conversion calculations. If calculating the overall conversion across multiple stages is important to the user, then the stages should be listed in the same order that they appear in the SRU. Once a stage is created, the feed streams and vapor product streams for that stage can be chosen by highlighting the streams in the Available Streams box and clicking the appropriate double-sided arrow button. If the user would like to use the reference streams defined in the Reference Feed Streams tab, then the checkbox Feed Streams Same as Reference Feed Streams can be chosen, which automatically populates the feed streams with the reference feed streams. With this new version, We have improved the management of stream callouts. The template manager can be used to create new templates or manage existing templates. Once these different stream callout templates have been generated, you can select the default or select which template to use. You can also drop callouts onto the flowsheet by right-clicking and selecting from either the default, choosing from one of the built-in templates, which include temperature, pressure, mass flow rate, acid gas loading, or acid gas parts per million values. Or you can access the template manager to either create a new template or to choose from one that you've already created. Once you have selected which callout you want, it will appear on the flowsheet, and then you can open the dialog box to further customize it if desired. Thank you for your attention, and we will be happy to take any questions you might have at this time.